Alright guys, this is lesson 3.2, and so we're in chapter 3. This is the second lesson in chapter 3. And the first lesson in chapter 3 was this new way of measuring angles with radians, and I think you're starting to get familiar with that and how big a radian is. A radian is almost 60 degrees. And so kind of a natural question is, we've got this way of measuring angles, this new way with radians. There was nothing wrong with degrees, but what would I ever use a radian for? Where are these used for? And one place it's used for is in calculus, but there's a couple formulas I can show you right now that use radians and use it in a much nicer way. The formulas come out much nicer when you're using radians than if you're using degrees. And so there's a couple formulas we can show right now, and that's what this section is about, just showing you a couple kind of nice applications where radians are a better unit to use than degrees. And so there's two formulas we're going to get here, and one of them is going to be for arc length, the arc length of a circle. And we're going to talk about that one. And then there's a second formula that will come up later. I think you look on page 6 or 7 or 8 of your notes there. There's also one for sector area. We'll talk about what a sector is and why you'd want to find the area of it. So the formula for arc length is this. It's S equals R times theta. S is going to be the arc length. And arc length is, if you think about a circle, that's not a very good circle, but use your imagination. The arc length is, part of the circumference. So say from here to here, and that's your angle theta. The arc length, which our book is calling L, our book is calling S, I just call it L, but it's really S, is that distance around the outside of a circle is the arc length. Okay? How do you get the arc length? Well, S, you take the radius, which is usually given, and you take it times the angle. But guys, this formula is only going to work if your angle is in radians. Then it works very nicely. If your angle is in degrees, this nice little formula here, S equals R times theta, it doesn't work in degrees. You need a different formula, a more complicated formula, if you're using degrees. So this is a nice little formula for radians. First thing, just as an understanding, and we'll practice using the formula, is where did this come from? It came from your formula for circumference. Remember circumference? The circumference of a circle is 2 times pi times the radius. And now that you've talked about radians, and a radian measure, radian is a radius, and in a whole circle, the angle in a circle, if you turn in a complete circle, is 360 degrees. Or now it's 2 pi radians. So now maybe you look at this formula, and you say, wait a minute, 2 pi, I thought that was a number. That's really an angle, and that's the angle. In terms of a circumference, that's the angle of a full rotation. So theta is really, 2 pi in this one, which is a full rotation. And so then you look back at your sector area formula and say, oh, that makes perfect sense. If I did a full rotation, I'd have 2 pi for theta. I have 2 pi r, which is circumference. And if I have a smaller rotation, pi halves, pi fours, 1 radian or whatever, I'll sub that in and I'll get that part of the circle. So we've got this formula. Arc length is the radius times the angle. Only works when your angle is measured in radians. So let's try this a couple times. So in the first application will be very straightforward, and then it'll get trickier and trickier. So here's a question. Find the arc length. I'll give you the radius. I'll give you the angle. And again, maybe just remind yourself, wait, what was the formula? Arc length is the radius times the angle. Is it really this simple? Yeah, I've got a radius of 12.3. I've got an angle of 2 pi thirds. As soon as I get this decimal, I'm thinking, oh, it's going to be a bit of a mess, so I'll pull up my calculator and figure this one out. So the radius times the angle. You could cross cancel if you want. Let me put that so we can see that better. Clear that picture off. And let's go 12.3 times 2 pi thirds. Looks good. And we'll get an arc length of 25, let's round that, well, let's go 25.76. So 25.76, and we rounded it, so that's about 25.76. And the units, whatever the units were, say the radius was in meters, then your arc length would be in meters. And again, what did we just figure out? Well, we figured out in a circle that has a radius of 12.3, if I turn an angle of 2 pi thirds, then the arc length. So if I was running around this track or something like that, I would have covered 25.76 meters. Is what we just figured out with the arc length. Okay, they could ask these questions backwards. Here's a circle. The radius is 3.2. This kid had an arc length, so they ran around 7. The question is, how big would that angle be? Well, not a difficult problem. Arc length is the radius times the angle. So the arc length is 7. The radius is 3.2. The angle we're going to figure out. This will be just division, right, to get the angle by itself. So let's go 7 divided by 3.2. And we get an angle. Ooh, 2 doesn't seem very big. But remember, it's 2 radians. So 2.19 radians. So we'll turn 2.19. We don't need units on it because the units are in radians. So 2.19 radians. And the same thing, you know, there's all the different variations here. What if I gave you the arc length and the angle? Could you find the radius of the circle? So again, here's some circle. Don't know the radius. I know this guy turned an angle of 2 pi thirds. I know this guy walked for 6. Again, let's give it some kind of units, 6 meters. The question is, what would the radius be from here to here? Well, arc length is the radius times the angle. Let's see, the arc length is 6. The radius I don't know. I wish I did. And the angle is 2 pi thirds. How would I get the radius by itself? Well, divide by 2 pi thirds. Let me just extend that a little bit. Divide by 2 pi thirds, or multiply by the reciprocal. So times 3 over 2 pi, both sides. Look, everything cancels out. So I get r equals, looks like 9 divided by pi. Does that look right? And let's just get a calculator value for that. And we've got 3 times 6 on the top, which is 18, divided by parenthesis. On the bottom, it looks like 2 pi. It's important that bottom is in a parenthesis. If you don't put that in a parenthesis, you're going to get the wrong answer. And I could have reduced that fraction, but 18 over 2 pi, and I get 2.86, roughly. So r is about 2.86. And again, whatever our units were, they'd be the same. So 2.86, and it looks like meters. So a very nice application of our formula. All right, let's use that formula one more time. And I'm here in class right now. The bell's going to ring on me in a minute, but don't worry, you guys can keep listening. Here's another nice application of the same problem, but now we've got latitudes. We can ask Mr. Lang, is it latitude or longitude? But we've got 2 cities, and we're assuming they lie just due north or south. So if you came, straight out of LA and started driving north, eventually you go through the United States, end up in British Columbia, and you end up in this town called Pennington. And so we're going to assume the book gave us a correct problem. It was just straight due north. And the question is, if I know this angle in between them, it's 36 degrees northern latitude, 49 degrees northern latitude, how far apart are the cities? And look, they give you the radius. So it seems like we have a radius. It seems like we have an angle. Could we get the arc length? All right, let's think about this a little bit. Let's think about the Earth. So there's our Earth. We have the equator for the Earth. And then these towns these cities are both in the northern hemisphere. So from the center here of the Earth, we have LA. And that angle is 36 degrees. Then we have this Pennington, which is further north. Makes sense. It's in British Columbia. And this might not be exactly the scale, but oops, there's a little typo there. We're just going to let that slide. And that angle is 49 degrees. So the bigger angle is 49 degrees. Told you the bell was going to ring. And then the question is, how far apart are the cities? So what is the distance right there of that arc? And hopefully you're thinking, same formula. Arc length is the radius times the angle. Arc length is the radius of the Earth this time, which is 6,400. Thank goodness we have units finally. 6,400 kilometers. And what's the angle between the 2 cities? Well, one is 49, one is 36. So in between the two cities is 13 degrees. So we're going to take 6,400 times 13, and that's degrees. Got to put our units on it. Okay, don't punch that into your calculator yet. Why not? Because we said this formula only works if theta is in radians. Well, latitude and longitude are measured in degrees, and so it makes sense we use degrees, but our formula is not going to work, and so we're going to have to go with our 6,400. We'll go with our 13, but guys, let's convert it to radians. And how do you convert it to radians? That was section 1. We'll multiply by pi over 180. So we have to make sure we're using radians. And then look, the degrees part will cancel out, and we're using radians. So very important when we use this formula, your theta always has to be in radians. So it's a nice little application of this. And again, let's punch this into our calculator. For an arc length, it wouldn't make as much sense to leave pi in your answer. It'd be like asking for somebody's height or something. You wouldn't give a pi in the answer for a height. So same thing for an arc length, it wouldn't make as much sense. So we got 6,400. I'll take that times 13 and a pi, and we'll divide it by 180. And I think in this you can see everything. You can see the 13, you can see the conversion with the pi over 180. Hit enter, and the distance between these two cities is 1,452 kilometers. And that makes sense if you think about driving, north-south in the United States. So 1,400, and I forgot it already, 1,452. So 1,452 kilometers. And a very nice application of our arc length form. That's an S, by the way, over here. So arc length is the radius times the angle. All right, there's one more of these to show you, and then another application, actually then a couple trickier problems, and then a different application with the sector area. But we are done with the first video.